for triangle similarity, and we're going to be proving that triangles are similar. So let's take a look at this math talk. So we just talked through in class a couple of different things about each of these. So the first one is how could we justify each of these statements? So how can we justify that triangle PQR is congruent to triangle STU? So these two orange ones, how do we justify that they are congruent? And so you could say something like side angle side, because they have two sets of sides that are identical. So 1 with 1, 1.5 with 1.5, and the angle between them are equal. So saying that the two triangles are congruent by side angle side. You could even say angle side angle, because you've got two angles and the side in between. So angle side angle would work as well. How are we going to show that triangle PQR is similar to STU? So how would we know that those are similar? So one thing you could think about is if the two angles are congruent here, okay, then this third one is going to have to be congruent. And then we see that the scale factor that brings this side to this side is 2. So the scale factor that brings this one to this one is also 2. And then because they're isosceles, we know that those side lengths are the same. So we also know that that third set of sides is in proportion as well. So all the angles are congruent and all the sides have a scale factor of 2, or they're proportional. So then taking a look at this next one, how could we tell that the two orange ones are congruent? Again, we see this mark here, so we've got that side angle side. And then how could we tell that these two are similar to one another? Okay, so the orange, whoops, guess that green is behind there, but this little green one and this big green one. So how can we tell that those are similar? So again, we've got two of the same angles. That's going to force the third one to be the same. And then we only have one side marked for us, but we could scale that open to this one. Okay, so we could scale, let me just move this a little bit. Okay, so we could scale this, right? So we could take whatever this side HG is divided by NM, and that would give us our scale. So that's going to open this side length here to this width. So then that's going to land H on G. Okay, and then those two triangles, that bigger orange triangle now, after we dilate this, that lands on here is going to be the same size as this one because of the angle side angle. We're going to scale this side to be the exact same length as this one. So then they would be congruent by angle side angle. So there's going to be a set of rigid motions with dilations that moves this triangle onto that one. All right, then let's take a look. So we're going to do a couple examples together before you put this in your book, so I can just kind of show you what this is asking. So this one is going to want us to draw two triangles, okay, that we can get them as different as possible given this characteristic. So in each triangle, one of the angles has to be 30 degrees. Okay, so I'm just going to start out by drawing this. Then we're going to need to have one of the angles be 30 degrees. So let me just set this on here, get a 30-degree angle. So here's 30. Oops, that's a little bit off. Okay, so we'll use that second dot. So that's 30 degrees. So anywhere along this ray right here will be 30. So I can kind of do whatever I want now. So I'm just going to go like this and then draw there. Okay, now I need to try and draw one that's as different from this one as possible. Okay, so as different as I can possibly make it. So I'm going to, again, start with a line. Okay, and then I'm going to set this on here. And I'm going to get a 30-degree angle. So then anywhere along this ray is where 30 degrees is. Okay, so this time I'm going to just shorten my original segment a little bit here. And I'm going to maybe do this. Okay, so that still has a 30-degree angle. So this one right here is 30 degrees. So each of those two triangles have 30 degrees, and they're as different as I could make them. Okay, so your goal is to get different triangles. All right, then in this next one, it says one angle in each triangle is 30 and another angle is 90. So this time we have to have the 30-degree angle. And so I'm just going to copy this. Okay, so here's a 30-degree angle. And now I need to have a 90-degree angle as well. Okay, so not only a 30, but I also need to have a 90. And again, remember, you're trying to get them as different as you possibly can. Okay, so I'm just going to start like this. Now we need a 90-degree angle. So I'm going to have this bottom length be my side of my triangle. So I'll measure up to 90 here. And then I'm going to have this be my other angle here. So I'll measure up to 90 for this one and draw in those segments. So there's to that 90. And then here's to this 90. So I need to extend this one a little bit further. All right, but then you can see the triangle here. So let me just redraw this in a different color since I did this one as a bold line. But we've got this triangle has a 30 and a 90. Okay, 30 being right here, 90 being right here. This one has a 30-degree angle here and a 90-degree angle here. All right, so tried to draw them as different as I could. And then down here, this last one says one angle in each triangle is 30 and another is 90. And the length of the pair of corresponding sides is 3 centimeters and 6 centimeters. Now I actually need to measure the side lengths. So then I'm going to lay this down. And so now I'm going to start out by getting these two sides measured at 3 and 6. So here's 3, and then I'll get, 6. And then go ahead and set your, protractor down to get a 30-degree angle. And I'm just going to copy it from here. This is a 30-degree angle. So let me just get that on there. And then this would also be a 30-degree angle. And then you need to measure to get your 90-degree angle. Okay, so this is 90 and 90. So then you can get those two triangles with those specific measures that this asked for. Okay, so that's just an example. So now in your book, you're going to be doing with some different angles. Okay, so this one had 30, 90, and this was 3 centimeters. This was 6 centimeters, with this being 30 and this being 90. So in your book, go ahead and do the characteristics that your book is asking for. Pause the video and then come back. So yours asked for one that had 2 triangles that were 45 degrees. One that had 45 and a 30, one set, so 2 triangles each. And then one that had a a 45-degree angle, a 30-degree angle, and then a pair of corresponding sides that were 2 centimeters and 6 centimeters. Okay, so just trying to get them as different as possible. And so you had some ideas from the examples that we kind of went through with some different numbers there. So what I want you to do is just make sure that you wrote that in your book. Okay, and now I want you to look at your triangles. Okay, and I want you to try to come up with, from your triangles, compare them. Now you really only, if you're doing this at home, only have your own to compare to, but let me copy these over. The example ones that we did onto here. So we have some to look at. So trying to decide which ones, okay, out of the ones that you drew, look like they have to be similar no matter what. Okay, what characteristics are you noticing in those that makes them look like they have to be similar? And try and write a conjecture for that. And so I kind of outlined it there at the bottom of the screen. So triangles with what seem to have to be similar no matter what. I've just got one more set to copy here. Oh, it's going to be off by a little bit. Let's get these words out of here. All right. So what kind of made them seem that they had to be similar? So what did you notice made it so that they had to be similar? Which ones look like they have to be, that they are similar of your drawings, even in comparison to mine? Okay, so that first set looks way off. Okay, so this one, number 1 looks like that's not right. Okay, but number 2 looks like those are similar. Like I could just expand this out. Okay, and that was one 45-degree angle and one 90-degree angle. Mine was 30 and 90, but yours was 45 and 90. Okay, and then in this next one, looks like those are similar as well. Okay, so looks like it started here at number 2. So triangles with 2 congruent angles appear to be similar no matter what. Or maybe down here you said 2 congruent angles and a side between. But it appears that this one actually makes it. So it appears that we don't even really need to know the side there. So let's go ahead and look at trying to prove that. Okay, so how could we prove that if it has 2 congruent angles, that the 2 triangles are going to be similar? Okay, so I've just got a set of triangles drawn here and labeled. So let's draw in and label a couple angles as being congruent. So how are we going to actually prove this? So how we're actually going to prove this is that we need to show that there's a sequence of rigid motions that takes one to the next. Okay, and if that happens, rigid motions and dilations, if we can prove that, then we've proven that it happens in all cases. And we don't want to put letters, or we don't want to put numbers to these, okay? So I've kind of put what we want to do. We want to look at the scale factors. We can dilate them to get them the same size, then translate it over and prove that the 2 triangles are congruent. So you can kind of do that backwards. Like you could start by translating if you want to, then dilate. Okay, that doesn't really matter. And let me group these together. Okay. So we can kind of watch this happen too. Okay, let's see which one goes on top of the other. All right, so we're going to translate. We're going to prove that PQR dilates to this purple one. Oh, and let me see. What did I do here? Okay, sorry. Let's try this one more time. All right. So I'm just going to follow the lineup here. So I'm going to say that we're going to dilate. And I'm going to dilate, like I said, I'm going to start with the orange one. Okay, so I'm going to dilate the orange one to the purple one. Okay, so dilate triangle PQR with Q, it doesn't really matter which center you do here, with Q as the center. And then we have to figure out the scale factor. So remember, scale factor, you divide image or dilation by original. Okay, so Q as the center and scale factor of, so pick which sides. So I'm going to pick these ones in between my two angles. So I'm going to say a scale factor of BC divided by QR. Okay, so whatever the length of BC is divided by whatever the length of QR is. Okay, so then I've dilated the triangles to be the same size. Well, I've dilated to get QR the same size as BC. Okay, so now translate triangle, or I'll say then I can triangle PQR by directed segment QB, whatever you want. Okay, so I would either do QB or RC to get these two angles that are congruent on top of each other. So what we just did is did this. Okay, and remember I've already dilated it as well. Okay, so let me duplicate this. Okay, so I've dilated it to get these two the same. Okay, so that's what I did first, was dilated it. Now I've moved Q onto B. Okay, so now Q is on top of B. Then we can prove that they're congruent now, because now this triangle will land right on top of it. Okay, then triangle PQR will land exactly on, so I said PQR, so PQR will land exactly on triangle ABC, because triangle PQR is congruent to, and this should really say A prime, B prime, C prime, because it's the dilation. Because PQR is congruent to A prime, B prime, C prime by angle side angle. Because we made QR be the same length as BC from our scale factor. So then they're going to land exactly on top of each other. So something similar to that for a proof. Okay, now again, like I said, you could translate first. You could translate PQR by segment QB first. Then you can do a dilation by scale factor BC over QR around point Q. And then you know that they will land exactly on each other because of angle side angle. So now QR and BC are the same size. You've got those two angles being congruent. So then they'll land on top of each other. All right. Are these triangles similar? Do we have enough information to tell? Okay, so we should now, based on our last proof, be able to look at just the angles. Okay, so if we subtract 100, because that's 40 and 60 from 180, we get that this angle equals 80. So then we see that we have two angles congruent. Okay, we've got this angle and this angle congruent to this one and this one. So we should be able to say automatically those two triangles are similar. You can also subtract these 120 from 180 and get 60 here. So what if we wanted to find the scale factor? Can we find the scale factor? And you can't find the scale factor when you just have the angle. So the scale factor requires some side lengths, and it requires corresponding side lengths. Okay, so if we had this one, if we wanted to do the scale factor from the little one to the big one, that would be 5/3. Okay, or if we were taking the big one to the little one, that would be 3/5. So depending on which way they're asking you to do the scale factor. So would we be able to find the missing side lengths now? Okay, and so remember we found out that this angle here is 80 and this one is 60. So would we be able to find the missing side lengths? Okay, now you'd have to know one of the other lengths, right? So we know that we can go, if we're taking this big shape to the small shape, the scale factor is 3/5. Okay, or if we're taking the small shape to the big shape, okay, this scale factor is 5/3. So we should just be able to multiply sides, but we need the actual side lengths. Okay, so if we had these two, so we were looking for x here, if we're given 8 in this bigger triangle, okay, so if we're given 8 in the bigger triangle, we should be able to multiply it by 3/5 to get that smaller length. Okay, so whatever you get when you do that. So this is really 8/1. So this would be 24/5, or the decimal version of that is 4.8. Okay, or if we were going to look for this one, this is in the bigger triangle. We have the smaller length. Okay, so we should be able to take that smaller length 6 and multiply it by the scale factor that brings the little one to the big one, which was 5/3. And that would equal 30/3 or 10. You can also set up proportions if you would like to. So if you'd like to start comparing side lengths and doing proportions, you can say x compares to 8. Okay, so then you can, when you write that out, you'd say x compares to 8. That should equal, when I do 3 compared to 5. Okay, so that should equal 3 divided by 5. And then you can cross multiply. Okay, so if we cross multiply, then you end up with that same proportion that we had, 24 divided by 5. And then you can do that again here. So if you're looking at 6 compares to y should equal 3 compared to 5. So we took a measurement here, small compared to big, and then small compared to big. And then you could cross multiply this and get 30 equals 3y and divide. You could also start with the y variable. So if you wanted to start here, you could say y over 6. So starting big to small. So y over 6 equals 5/3. So there's all sorts of different proportions you could set up. Again, you still get 30 divided by 3, and you get 10, just like we got there. All right, so what we found out today is that we've got angle, triangle similarity theorem. So if you've got two pairs of corresponding angles in a triangle, then those triangles are similar. Okay, so all you have to do is see two sets of angles being the same, and then you know that the triangles are, in fact, similar. Don't need to know any lengths. Okay, just need to know this, and you automatically know that they are similar. All right, and then you can get this written in your reference chart, angle similarity. So in this one, in fact, I just would have had to have given you A is congruent to C on the picture, and then you can come up with vertical angles yourself. Okay, they do have them marked in here for you, but if they just had it drawn like this, okay, they would only have to give you those angles, and you would know vertical angles. So then the triangles are similar. And then lesson summary. So two angles of one triangle are congruent to two angles of a second. Then those triangles are similar by angle similarity theorem. So if you take a look in this diagram, this is a diagram of two triangles being similar by angle, because we can see the two sets of angles. B is congruent to E, A is congruent to D. And then they go through a proof of that again. Okay, so they talk about the scale factor. So then you're going to dilate this one on the scale factor of the ratio of this side to this side, which will shrink it down to the same size. then you know that A prime, B prime is congruent to DE, and the two angles are equal. So that dilated shape is the exact same size as this one. Therefore, it'll land exactly on top of it, meaning it's similar. So that's kind of what they go through in the rest of that.